Have you ever looked closely at a map of the U.S., maybe zoomed in on Idaho? You see that huge kind of crescent shape cutting across the south. That's the Snake River Plain. And it's way more than just flat land. It's this incredibly dramatic landscape, really sculpted by these massive forces deep inside the earth. Today, we're doing a deep dive into the Snake River Plain, trying to unravel its really complex geology. We'll get into how the Yellowstone hotspot, that powerhouse under Yellowstone Park, how it actually carved out this whole region. Then we'll explore the really distinct geological stories playing out in its western part versus its eastern part. They're quite different. We'll look at the incredible variety of volcanic activity, which is just amazing, and even touch on how these deep geological forces impact things like groundwater, which is vital, and potential hazards for people living there today.
Right. And our mission here is basically to dig into some key research, papers like Tectonic and Magmatic Evolution of the Snake River Plain Volcanic Province, and another called Snake River Plain Volcanism, Hotspot, Tectonics, and Hydrology. We want to pull out the most important nuggets so you get a real sense, not just of what happened over millions of years, but really why it matters for the landscape you see today.
Okay, fantastic. Let's unpack this incredible story. Where should we start? Maybe with the big driver, the hotspot itself. Yeah, the Snake River Plain is, well, it's fundamentally tied to the Yellowstone hotspot. That seems pretty clear. But where did this whole fiery journey actually kick off?
Well, the current thinking among scientists is that the Yellowstone hotspot probably first surfaced way down in northern Nevada. We're talking about 16 million years ago. You have to picture this ancient volcanic field forming near the Nevada-Oregon border. It's called the McDermott Field. It's rhyolites. Those are the really thick, sticky volcanic rocks. They date back to 16.1 million years. And they represent the oldest set of these giant collapsed volcanoes, or calderas, that we see along the hotspot's trek. So yeah, many researchers think that area is, roughly where this massive upwelling of hot rock from deep inside the earth, what we call a plume head, first really arrived.
A plume head. So this wasn't just some gentle leak. This sounds like a truly colossal event, a huge blob of superheated rock pushing upwards. Do you know how fast this thing was moving?
Yeah, geologically speaking, it was moving pretty fast. The model suggests the plume was rising at about maybe zero 0.1 meters per year, which sounds slow, but that translates to 100 kilometers every million years. And you can trace that back to when it first hit the underside of the North American plate, probably around 17 million years ago. Just to give you a sense of the scale, we estimate the volume of this plume head, just in the upper mantle part, was maybe around 400 cubic kilometers.
400 cubic kilometers. That's incredible. An unbelievable amount of material.
It is, enough to explain things like the massive Columbia River flood basalts in that huge Nevada rift zone.
So this hotspot didn't just spew lava, it actually interacted with the crust it was moving under. It sort of shaped how the continent itself behaved, didn't it?
Oh, absolutely. That's a critical point. The kind of crust that was already there really dictated where and how this magma could erupt. You see, as this plume moved northeast, it encountered this interesting transition. To the south, you have older, thicker, crutonic crust, the real ancient, stable core of the continent. But as you go north, the crust gets younger, thinner, more like oceanic crust, actually. And that denser, more iron-rich northern crust basically made it easier for the basaltic melts, which are also iron-rich, to, punch through and erupt. It's why nearly all the Columbia River basalts, for instance, erupted through fissures in that thinner crust area. The very first eruptions seem to have followed this north-south line, a sort of geological seam, just west of that really old Precambrian crust.
And the sheer force of this plume head arriving, it pushed the land up, right?
Yeah.
And that changed how the crust itself tore apart.
Exactly. The uplift was significant, and it led to some slightly unusual patterns of rifting or cracking. Instead of the sort of typical three-armed rifts you sometimes get, spreading out at 120 degrees, here we saw more pronounced north-south tearing. That was likely related to how the stresses were oriented in the crust at that time, east-west. And this uplift, this change in elevation, it also had a profound impact on the climate and the plants over millions of years. As the land rose and then later subsided, you saw this shift from, say, Miocene forests with deciduous trees and conifers to later Pliocene forests with grasslands, and eventually to the much drier steppe and alkaline lakes we find evidence for in the Pleistocene. There's even some isotopic evidence from old lake beds and volcanic glass suggesting parts of the western Snake River Plain were significantly higher, maybe around 7 million years ago.
It's amazing how interconnected it all is. So the hotspot is the big story, but you mentioned the plain itself isn't uniform. It has these two distinct parts, west and east. Let's dive into the western Snake River Plain first. What's its story?
Okay, so the western Snake River Plain, Fundamentally, it's this long, relatively narrow basin, maybe 70 kilometers wide, 300 kilometers long. Think of it like a big trough. And it's mainly formed by what we call normal faults. That's where the crust pulls apart and blocks slide down relative to each other. This stretching, or extension, accounts for maybe 10% of the basin's width, which is actually similar to other big rift basins around the world, like Lake Baikal in Russia. We can see from rocks at the surface and seismic data that the basin floor dropped up to 2 kilometers relative to the sides. That's due to both the faulting and this broader downward bending or down warping. Now, its origin is mostly tied to the bigger picture of the Basin and Range province, that huge area of the western U.S. that's been stretched and faulted. So while it's near where the hotspot started, its formation is considered, more indirectly related to the hotspot itself. It really got going around 15.3 million years ago.
Right, so it's really part of that bigger basin and range stretching story. But you also mentioned sideways movement. It wasn't just pulling apart.
Exactly. There's also evidence for a significant right lateral stripe slip component. That means blocks of crust were also sliding past each other horizontally towards the right. This was happening around the same time that this sunken block, the Oregon-Idaho graben, was forming. You can see these complex structures involving both pulling apart and sliding sideways in places like the Wallula Fault Zone. They often form these elongated features with deep basins and faults running along their edges. And if you look at magnetic maps of the area, you see these broad stripes of high magnetism, which probably indicate thick layers of flood basalt and intrusions of solidified magma deep down. But you also see these distinct circular bullseye lows in the magnetic field, which often pinpoint the locations of old collapsed volcanoes' calderas. And geologically, this whole area kind of straddles a major boundary. It's a suture between the ancient core of North America and younger bits of land that got stuck onto it over time.
Fascinating. And what about deep down? You hinted at something unusual. I think I read about weird density anomalies under the Western SRP.
Ah, yes, that's a really key observation. There's a very noticeable positive gravity anomaly over the Western Plain. Basically, gravity is slightly stronger there than you'd expect. And what that tells us is that deep down, probably from about nothing to maybe 18 kilometers depth, there's a large body of very dense rock. We think it's likely solidified basalt or gabbro, much denser than the typical granitic rock you'd expect in continental crust. It's like finding a huge, heavy brick embedded deep underneath. It means the deep structure there isn't typical granite. It's dominated by these intrusive volcanic rocks.
Okay, that paints a picture of the deep structure. And this western area was also, for a long time, filled with a massive lake, wasn't it? Lake Idaho.
That's right. The concept of a large, long-lasting lake is definitely accurate. The main rock layers that tell its story are the Chalk Hills and Glens Ferry formations. They're quite similar lithologically, and they span a long time, from the late Miocene, say, around 12 million years ago, right through the Pliocene. This lake apparently rose to higher levels over time, became more alkaline, and then eventually, around 4 million years ago, it reached a point where it could spill out, and it began this slow, gradual process of draining away.
Okay, so that's the west. Basin and range extension, some strike slip, deep, dense rocks, ancient lake. Now let's pivot. The eastern Snake River Plain. How is its story fundamentally different?
It's a really stark contrast, actually. In the eastern SRP, the pulling apart, it's mainly expressed by this broad downward bending, this down warping of the crust. You don't see the extensive, obvious faults bounding the plain like you do in the west. But the amount of subsidence is huge. We're talking over 2 kilometers of drop at the surface, and maybe up to 8 kilometers of structural drop deeper down, and you can even track a gentle southwestward slope in elevation along its axis. It's like the whole plain is subtly tilted downwards towards the southwest.
8 kilometers of structural release. So what's causing all that sinking? Why is the crust dropping so much in the east?
Well, researchers have put forward a few main ideas, likely working together. One is simple thermal contraction. As the hotspot moves away, the crust cools and shrinks, causing it to subside. Another is crustal densification. This is the idea that lighter crustal rocks are effectively replaced or intruded by denser, iron-rich magma from below, making the whole column heavier and causing it to sink. And related to that is isostatic readjustment, basically, the crust flexing downwards under the immense weight of this added dense material. A key part of this is thought to be a massive mafic sill, a huge flat sheet of solidified dense magma emplaced deep in the crust, maybe around 10 million years ago. This sill would have provided the heat needed for the rhyolitic volcanism we see in the east, and its sheer weight plus ongoing additions from younger dikes and sills causes that sinking. And we have some direct evidence from deep drill holes. They've hit rhyolite dated at 8 to 8.5 million years old at depths of, 1.5 to over 3 kilometers below the current surface.
Wow. drilling down and finding 8 million-year-old surface rock 3 kilometers deep. That really shows the subsidence. And the faulting style is different too, you said, even if it's less obvious.
Exactly. If there are major normal faults along the northern edge of the eastern SRP, like those defining the western plain, they're mostly buried and hidden by younger volcanic rocks. But importantly, if you look just outside the eastern plain, in the adjacent Basin and Range province, you see very large, very active normal faults. Things like the Lost River Fault, the Lemhi Fault, the Beaverhead Fault. These show significant extension, maybe 10–15%, stretching across that part of Idaho. These faults dip fairly steeply, maybe 50 degrees, and go deep down to 16 kilometers or so. So the active faulting is happening right next door, but the plain itself seems to be responding mainly by sagging downwards.
Okay, the structural difference is clear. Now let's get back to the magma itself. The Snake River Plain is, well, it's volcanic country. Let's talk about the eruptions, starting with those really thick, silicic, rhyolitic ones.
Yeah, and our understanding of those has really evolved. If you look at places like the Juniper Mountain Volcanic Center, the early thinking often was that these widespread silicic rocks were rheomorphic agimborites. That means they started as explosive ash flows, but then got so hot they started flowing again like lava after they landed. But more recent work suggests something different for many of them, that they're actually incredibly voluminous silicic lava flows, just enormous, slow-moving rivers of incredibly thick, viscous lava. They have features that really point to them being emplaced as liquids, albeit very, very sticky ones. The rhyolite of Petition Reservoir, for example, dated around 13.8 million years old, is now thought to be one massive lava flow from a local vent.
That's a major reinterpretation. Not explosive ash, but huge, slow flows. What about the chemistry? Can that tell us more about where these rhyolites came from?
Oh, definitely. The chemistry is like a fingerprint. Take the tuff of McMullen Creek, for example. It shows internal chemical variations that tell us it underwent fractional crystallization before it erupted.
Oh.
Basically, as a magma sat there cooling slightly, different minerals crystallized out, changing the composition of the remaining melt. What's also interesting is its lead isotope signature. It's actually more similar to the basalts found in the eastern Snake River Plain than it is to the rhyolites up in Yellowstone National Park. That suggests, distinct plumbing systems, distinct magmatic origins, even within the broader hotspot track. Yellowstone rhyolites, on the other hand, they show these extreme depletions in certain elements, barium, strontium, titanium, stuff like that. That points to really extensive processing and evolution within the crust, a long crustal history before eruption. It suggests those magmas started crystallizing almost immediately as they rose.
Okay, moving west again to the Auwai front. How do the rhyolites there connect back to that ancient Lake Idaho we talked about?
That's a neat connection. The rhyolite units along the Auwai front, they date mostly between about 11.7 and 11.0 million years ago. This includes things like the Jump Creek rhyolite field and the Wilson Creek ignimbrite. And the timing seems to line up with evidence for a steady lowering of Lake Idaho's level between about 12 and 11 million years ago. It's like the volcanic activity was potentially responding to the changing water levels and pressures. And then there's a younger group, the Cerro El Otoño group. It seems to represent maybe the last little bits of this silicic magma system just kind of oozing out along the edges of the widening western SRP graben, like the system was winding down.
Fascinating interaction between volcanism and the lake level. Okay, let's shift gears to the much more common volcanic rocks in the SRP.
Yeah.
The basalts. They seem to tell a really diverse story, too.
They absolutely do. And what's striking is that almost all the basalt volcanoes you see in the Western Plain, the Oahe Plateau, the Central Plain, they're monogenetic, meaning each volcano erupted only once. But once could mean a lot of different things. Their forms are incredibly varied. Simple shield volcanoes, complex ones, vents that were just fissures or dikes, cinder cones, spatter cones, tough rings formed by steam explosions, maars.
Mars. What are those again?
They're these broad, low-rimmed craters, often filled with water, formed by really explosive interactions between magma and groundwater, phreatomagmatic explosions, and even complexes where magma erupted directly underwater. The style really depended heavily on whether water was around. Dry environment. You get your classic, relatively quiet Hawaiian-style lava flows, lots of groundwater available. You could get these really violent, steam-driven Surtsian-style eruptions.
So water is a huge factor in the eruption style and the landform. And the basalt composition itself changes too, right? Giving us more clues about the plumbing.
Exactly. The chemistry varies quite a bit, telling us about different sources and processes. In the Western SRP, the basalt eruptions happen mostly between about 2.2 and zero point 0.4 million years ago. And during that time, you see this shift from eruptions happening underwater or near the water surface to eruptions happening entirely on dry land as the area dried out after Lake Idaho drained. And chemically, during the Pleistocene epoch, roughly between 1.2 and zero point 0.8 million years ago, the basalts tended to become richer in iron. We call them ferrobasalts. But then, around zero point 0.8 million years ago, there was a shift towards basalts with lower iron, but enriched in alkali elements.
Okay, so what are those chemical shifts, like becoming iron-rich then alkali-rich? Tell us about where the magma was coming from, deep down versus shallower.
It gives us really good clues. For example, those later Pleistocene alkali-rich basalts found in the Melba area, chemically they look a lot like oceanic island basalts, or OIBs, the kind you find in places like Hawaii. That strongly suggests they were derived from a deeper source, tapping into the asthenospheric mantle, that hot, flowing layer beneath the plates. In contrast, some of the older basalts seem to have come from shallower lithospheric sources, the rigid plate itself. They carry chemical signatures inherited from those sources, not just from mixing with shallow crustal rocks on the way up. And for the eastern SRP basalts, the data generally points towards them forming from different degrees of melting within an enriched subcontinental lithosphere, basically. Old mantle material stuck to the base of the continent with maybe some minor processing, like olivine crystallizing out in the crust before eruption. The overall chemical variability really suggests there wasn't just one single source, but multiple slightly different magma batches coming up from heterogeneous sources.
That's incredibly detailed information just from the rock chemistry. Now, I'm curious about something you mentioned earlier. What happens when lava meets water, creating that water-affected basalt? What exactly is that?
Right, WAB. It's an interesting material. It doesn't form just one way. It could be the salt that erupted on land but then got submerged in water and cooled slowly. Or it could be altered by hot water or steam circulating from nearby wet sediments or other flows. A really key characteristic, especially if it's heavily altered, is that it develops tons of these tiny, closely spaced crackle fractures running through it. And what that means is when this WAB gets exposed at the surface and starts to weather, instead of staying as solid rock, it tends to just crumble apart into this gravelly, grus-like stuff made of small fragments.
Well, it looks really different and behaves differently when it weathers.
Exactly. But what's surprising is that chemically, despite these big physical changes, the process is mostly isochemical hydration. That means the rock is basically just absorbing water, but its overall major element chemistry doesn't change much, it just gets hydrated and weakened.
Okay, that makes sense. So all this complex geology, the faults, the subsidence, the different lavas, the interaction with water, how does this impact people today, particularly thinking about water resources and potential hazards? Let's talk aquifers first.
Yeah, absolutely critical. The Snake River Plain, especially the eastern part, holds a hugely important aquifer system, mostly within those basalt layers. Understanding how water moves through it is vital. Scientists use all sorts of data logs from old deep holes drilled for oil and gas exploration way back, plus core samples and data from research facilities built right on the plain, like at the Idaho National Engineering and Environmental Laboratory, INEL, and at sites like TAN and CPP. All this data helps map out the features within the basalt that control permeability, how easily water flows. Things like those bubbly vesicular zones in the lava, the rubbly zones where different lava flows contacted each other, and of course, fractures.
So the permeability, how water flows, must be incredibly patchy and complex. That it's not like water flowing through uniform sand.
Not at all. It's highly complex. We've identified sort of two main types of high permeability features in these basalt flows, especially the inflated ones. You've got what we call type 1 zones. These are highly porous, rubbly zones right at the contacts between individual lava flow lobes. But their extent is limited by how big those lobes were, so they can be quite patchy, like finding scattered pockets where water flows really well. Then you have type 2 zones. These are actual networks of fissures or cracks within the main body of the inflated lava flows. These potentially offer much greater lateral continuity pathways extending over larger distances, but they can also be anisotropic, meaning water might flow much better in one direction than another, following the fissure network. And what's really wild is that the geometry of these lava flows and the fissure networks within them has actually been found to be fractal.
Fractal, like those repeating patterns you see in snowflakes or coastlines.
Exactly like that. They exhibit self-similar patterns across different scales. A small-scale crack network might look geometrically similar to the large-scale layout of the flow fields. And that's incredibly useful because it means we can potentially infer small-scale details about permeability, which are hard to measure everywhere, by looking at the larger-scale patterns we can map.
That's amazing. Using fractal geometry to understand groundwater flow in basalt. Wow.
Oh,
Okay, but switching from water resources to hazards.
yeah.
For people living on or near the plain, what about future volcanic activity? Is that a concern?
It's definitely something geologists monitor and assess. We can estimate the probability or recurrence rates for eruptions in different zones. For instance, within the Ineal area, there's what's called the axial volcanic zone near its southern boundary. The estimated recurrence rate there is about 6 times 10 to the minus 5 per year, which translates to an average time between eruptions of somewhere around 16,000 to 17,000 years for that specific zone. There's another older zone, the Howe East Butte Volcanic Rift Zone, mostly covered now, which has a much longer estimated interval, maybe around 100,000 years. So these are long time scales, but not infinite.
Okay, 16, 17,000 years on average for the more active zone. That puts it in perspective. And for specific facilities like the Central Facilities Area, the CFA at Ineal, what's the main risk if an eruption did happen nearby?
Right. The CFA itself is about 15 kilometers away from the known vents in that axial zone. Because of that distance and the local topography, things like volcanic ashfall or tephra or significant gas exposure or even ground cracking from a dike getting close, those are considered unlikely direct impacts. The primary hazard for an area like the CFA is potential inundation by lava flows should an eruption occur upslope.
Lava flows. Okay, that sounds serious. Is there likely to be any warning if that were going to happen?
Yes, and that's actually relatively good news based on analogies with currently active basaltic rift zones like in Iceland or Hawaii. We know that magma often takes considerable time, weeks, sometimes months, to travel up from the deep source regions in the upper mantle, maybe 50 to 200 kilometers down. Based on that, the estimate is that perhaps 80% of potential future lava flows in this region would likely provide at least 1 month of advanced warning. That upward movement of magma can usually be detected by seismic networks monitoring for small earthquakes and ground deformation.
A month or more of warning.
Hmm.
That's significant.
It is. And then once lava actually erupts onto the surface in low relief terrain like the southern Ineal, basaltic flows tend to move relatively slowly. We're generally talking less than several kilometers per day. Even the faster moving Hawaiian Pahuho flows average maybe around 5 kilometers per day. So that combination of warning time and relatively slow advance speed does allow for potential mitigation planning and efforts if necessary.
That's somewhat reassuring. So wrapping this all up,
Mhm.
what are the big takeaways here? We've gone on this incredible journey through the Snake River Plains geology. It's this landscape just fundamentally shaped by these colossal forces from deep inside the earth. You have the migrating Yellowstone hotspot literally burning its track across the continent. You have the distinct ways the western and eastern halves have stretched and sunk. And then just this incredible variety of volcanic eruptions building the plain up over millions of years. It's really a testament to how dynamic our planet is.
Absolutely. We've seen how ancient lakes grew and shrank in response to these geological shifts. We've seen how the chemistry of the basalts acts like a tracer, telling us stories about where the magma came from deep below, and even how the fine details, like the internal structure of lava flows and how they interact with water, can have really significant impacts on something as vital as groundwater resources today. The story of the Snake River Plain really is one of constant ongoing change, driven by this powerful, deep-seated geology that's definitely still active.
So next time you look at a map of the American West, maybe you won't just see the Snake River Plain as, just a flat bit of Idaho. You'll see it as this huge, active geological laboratory, this scar telling an amazing story.
And maybe think about this. Given these powerful geological processes, we've talked about the moving plates, the rising magma, the crust constantly reshaping itself, what entirely new landscapes might be slowly, maybe silently, forming right now, deep beneath our feet, unseen in places just like the Snake River Plain. What's next?
That was a great thought to end on. Thanks so much for joining us on this deep dive.